We tunnel right into the core of fascinating subjects to really get to the heart of things.
That's the goal.
And today, we're diving into one of humanity's oldest questions, really.
Yeah.
What is everything made of? From ancient Greek thinking about atoms to modern physics. It's been a long road.
It really has, a fundamental quest. And our mission today is to explore that whole universe of particles, the fundamental ones and the ones they build up, but looking at it through a specific lens.
Mass.
Mass. Okay, that sounds simple, but I suspect it's not.
Well, exactly. A particle's mass isn't just, how much it weighs. It's packed with information about what the particle is, how stable it is, how it interacts, its whole role in the cosmos.
And we can even talk about mass in terms of energy, right? Thanks to Einstein, EMC of fear.
Precisely. That's the language particle physicists use.
Mm-hmm.
And the range is just staggering. We're talking more than 11 orders of magnitude difference in mass.
11 orders. Wow. From what to what? From neutrinos, which are almost massless, just ghosts passing through us, all the way up to the top quark, which is incredibly heavy for a fundamental particle, a real heavyweight.
Okay, so what's the plan for today's deep dive? How are we tackling this?
Well, first, we need the foundation. That means understanding the standard model, the basic theory.
Right.
Then we'll climb what you could call the mass ladder. We'll go through the elementary particles from lightest to heaviest.
Okay.
After that, we look at the composite particles, the ones that actually make up, well, you and me and everything we see.
Protons, neutrons, that sort of thing.
Exactly. And finally, we'll peek beyond that into the realm of hypothetical particles, the ones physicists think might be out there, solving some of the big remaining puzzles.
So this isn't just abstract physics. It connects to everyday reality.
Absolutely. This is about the building blocks of everything. You'll get some surprising facts, maybe some aha moments. It should leave you with a much clearer picture of fundamental reality.
Sounds great.
Yeah.
Let's dive in. Where do we start? The standard model.
Yes, the standard model. But the first thing to grasp is that it's not about tiny balls flying around. It's a quantum field theory.
Fields. Okay, what does that mean practically?
It means reality is made of fundamental fields spread throughout all of space and time. Think of them like invisible oceans. And particles, they're like localized ripples or excitations in those fields. Quanta.
Ripples in cosmic oceans. I like that. And these particles, these ripples, they fall into categories.
Two main ones, fermions and bosons. The difference comes down to their spin, their intrinsic angular momentum.
Like a spinning top.
Sort of, but it's a quantum property. Fermions have half-integer spin. They're the matter particles, quarks and leptons. And crucially, they obey the Pauli exclusion principle.
Ah, I remember that from chemistry. No two electrons in the same state.
Exactly. That's the Pauli principle at work. It means fermions take up space. It's why atoms don't collapse, why electrons form shells, and why we have the whole periodic table and, well, chemistry.
Okay, so fermions are matter. What about bosons?
Bosons have integer spin. They're associated with forces and also the origin of mass, as we'll see. Unlike fermions, bosons can pile up in the same state. Think of a laser beam that's just countless photons, which are bosons, all doing the same thing.
So bosons include force carriers?
Yes, the gauge bosons, and also the Higgs boson, which is special.
Got it. And the standard model includes forces, right? 3 of them.
3 fundamental forces, yes, leaving gravity aside for now. And these forces work by exchanging gauge bosons. First, there's the strong nuclear force.
What's the strongest one?
By far, but only over incredibly short distances. It's mediated by gluons, and it's what binds quarks together inside protons and neutrons and holds atomic nuclei together, cosmic glue.
Okay.
Then the electromagnetic force, mediated by photons. This governs anything with electric charge light, electricity, magnetism. It holds atoms and molecules together. Basically, all of chemistry and biology relies on it.
Pretty important then. And the third?
The weak nuclear force, mediated by W and Z bosons. This one's responsible for things like radioactive decay, beta decay specifically. And it's unique because it can actually change the type or flavor of a particle.
Changes flavor, like
Right.
a quark turns into a different kind of quark.
Exactly, like a down quark changing into an up quark. It's a fundamental transformation.
Wow. Okay, so forces, particles.
Mm-hmm.
But you mentioned a problem earlier. The theory initially needed particles to be massless.
Yeah.
How did that get fixed? We know things have mass.
Right, that was a huge theoretical hurdle. The solution, proposed back in 1964, is the Brout-Englert-Higgs mechanism, usually just called the Higgs mechanism.
The Higgs field. I've heard of that.
It suggests there's this invisible field, the Higgs field, everywhere in the universe. And unlike other fields, its baseline energy level isn't zero. It has a value.
Okay, yeah.
So particles moving through this field interact with it. They experience a kind of drag. And that interaction, that drag, is what we perceive as mass.
So a particle that interacts a lot with the Higgs field gets a lot of mass.
Precisely. And one that barely interacts gets very little mass. And particles like the photon, which don't interact with it at all, stay massless.
And the Higgs boson, discovered in 2012.
That's the ripple in the Higgs field, the quantum excitation. Finding it was the confirmation that this whole mechanism is likely correct.
Okay, but you also said mass is more nuanced, something about bare versus dressed mass.
Right. For particles like electrons, which can exist on their own, their mass comes straight from the Higgs interaction. That's their bare mass. But quarks are trickier.
Because they're always stuck inside other particles. Color confinement.
Exactly. They're never found free. Inside a hadron, like a proton, a quark is surrounded by this cloud of virtual gluons and other quark-antiquark pairs. This cloud adds to its effective mass, making its dressed mass much larger than its bare mass.
Okay, that makes sense. But then there's the proton itself. You said something mind-bending about its mass earlier.
Yes, the proton mass paradox. This is really fundamental. A proton is made of 2 up quarks and 1 down quark. If you add up their bare masses, the ones from the Higgs interaction...
It doesn't add up to the proton's mass.
Not even close. It's only about 1% of the proton's total mass.
1%. So where does the other 99% come from?
It comes from energy, specifically the energy of the strong force holding the quarks together. It's the kinetic energy of those quarks whizzing around inside that tiny space, plus the potential energy stored in the gluon field acting like stretched rubber bands between them.
So, EMCF in action, the energy is the mass.
That's exactly it. Most of the mass of the stuff you're made of isn't from the Higgs field giving mass to the fundamental bits. It's from the sheer energy binding those bits together. It's an emergent property.
That's incredible. So the Higgs gives the seeds, but the strong force energy provides the bulk for everyday matter.
For profound asymmetry, yeah. And what's also key is the standard model doesn't predict these masses or the strength of the Higgs coupling. We have to measure them. Their inputs, parameters, and their specific values are, well, clues that there might be deeper physics we haven't found yet.
Okay, framework established. Shall we start climbing that mass ladder? From 0 up.
Let's do it. At the very bottom, mass equals 0 eV, the massless realm. These particles have to be massless because of the underlying symmetries of their forces. Like the rules are just set up so they can't have mass.
First up.
The photon, symbol gamma, the quantum of light, carrier of the electromagnetic force. Its masslessness is why electromagnetism has infinite range. We can see stars billions of light years away because photons don't have mass.
Einstein's idea from 1905, right? The photoelectric effect. Realized light comes in packets.
Exactly, a cornerstone of quantum mechanics. And as we said, responsible for pretty much all chemistry and biology.
Okay, who else is massless?
The gluon, symbol G, the carrier of the strong force gluing quarks together. It's also massless. But unlike the photon, gluons carry the strong force charge themselves color charge.
What does that mean, they carry the charge?
It means gluons interact with each other, not just with quarks. This self-interaction is bizarre and leads to color confinement. The force between quarks doesn't get weaker with distance, like electromagnetism. It gets stronger, like stretching a rubber band.
So you can't pull a quark out on its own?
Nope. Try to pull them apart, and the energy in the gluon field gets so high it's easier to create a new quark-antiquark pair out of the vacuum. The original quark stays confined. We only see the effects indirectly, like in jets of particles and colliders.
Indirect confirmation came in the late 70s.
1979 at the DSY lab in Germany, yeah. So too fundamental massless force carriers.
Okay, moving slightly up the ladder. Still tiny mass, but not zero.
Right. The whispers of mass. Less than 2 electronvolts. This is the realm of the neutrinos. 3 types: electron neutrino, muon neutrino, and tau neutrino.
The ghost particles.
Pretty much. Incredibly tiny mass, no electric charge. They only interact via the weak force and gravity, which are both, well, weak. So they can pass through light years of lead without stopping. Trillions stream through you every second from the sun.
And finding out they have mass was a huge deal, wasn't it? A crack in the standard model.
A massive deal. For decades, the standard model assumed they were massless. But then came the discovery of neutrino oscillation experiments, like at the Sudbury Neutrino Observatory, showed neutrinos changing from one type to another as they travel.
And they can only do that if they have mass.
Exactly. Oscillation requires mass differences between the types, so they must have mass. It was the first definitive experimental proof of physics beyond the standard model, because the original model had no way to give them mass. It spurred all sorts of new theories, like the seesaw mechanism, to explain why their masses are so incredibly tiny compared to everything else.
A genuine puzzle piece we didn't know was missing. Okay, next rung.
Now we get to the first generation of matter, the absolute foundation of all stable stuff around us. First, the one we all know, the electron ELAC. Mass about 0.511 MeV.
Half a MeV, okay?
Negatively charged, orbits the nucleus, defines all of chemistry. J.J. Thomson found it in 1897, the first subatomic particle. Showed atoms weren't indivisible.
And its partners in this generation are quarks.
The up quark and the down quark. Masses are roughly 2.2 MeV for the up and 4.7 MeV for the down. Though remember, these are bare masses. Their effective mass inside protons, neutrons is much larger.
Right.
Proposed by Gell-Mann and Zweig in '64, confirmed at SLAC around '68. A proton is 2 ups and a down. A neutron is 1 up and 2 downs.
And just those 3 up-down electron make up basically all ordinary matter. Stars, planets, people.
That's the incredible thing. All the stable matter you see and interact with is built from just these 3 fundamental particles. Simplicity at the core.
But nature didn't stop there. There's a second generation. Heavier copies.
Exactly. The second generation. Heavier, unstable versions, not found in normal matter, but created in high-energy collisions, like from cosmic rays hitting the atmosphere or in particle accelerators.
Nursed.
This strange quark, about 96 MeV. It got its name because particles containing it, found in cosmic rays in the 40s, lived surprisingly long before decaying. They seemed strange.
Why did they live longer?
Because the strange quark has to change its flavor via the much slower weak force to decay into lighter up or down quarks. That delay was a big clue about quark types and the weak force.
Okay. Who else is in generation 2?
The muon. About 105.7 MeV, basically a fat electron, 207 times heavier. That extra mass makes it unstable. It decays in about 2.2 microseconds.
And its discovery was a surprise? Who ordered that?
That was I.I. Rabi's famous line, yeah. This just didn't seem necessary in the theories at the time, 1936, just a heavy electron copy.
And the last member of generation 2?
The charm quark. Much heavier, around 1.27 GeV, that's giga-electronvolts now. Its existence was actually predicted theoretically in 1970 to solve a puzzle about certain weak decays that should have happened but didn't.
A theoretical fix.
Yes, the Jim mechanism. Finding the charm quark in 1974, the November Revolution, the J particle, was spectacular confirmation of the quark model. It really cemented the whole picture.
Which brings up that listener question you mentioned. Why are there these heavier copies? Why 3 generations? Nature seems redundant here.
It's one of the deepest mysteries in particle physics. We don't know why. It points towards some underlying pattern or symmetry we haven't figured out yet.
Okay, on to the third and presumably heaviest generation.
The third generation. Even heavier, even shorter-lived. First, the tau lepton, another electron cousin, but way heavier, about 1.777 GeV. That's almost 3,500 times the electron mass. It decays incredibly fast in like 10 opal-kicans. Found in the mid-70s.
And its quark partner.
The bottom quark, also called beauty, around 4.18 GeV. Its existence, along with the top quark, was predicted in 1973 by Kobayashi and Maskawa to explain a subtle asymmetry between matter and antimatter known as CP violation.
So, needed to explain why there's more matter than antimatter in the universe.
It's a crucial ingredient in the standard model mechanism for CP violation, yes. Finding the bottom quark in 1977 was strong evidence for the existence of this third complete generation.
Okay, we've covered all the matter particles, the fermions. What about the heavy bosons? The weak force carriers.
Right, climbing higher in mass now, the W boson. Mass is about 80.37 GeV. It comes in positively and negatively charged versions. It mediates the charged current-weak interactions, the ones where flavor changes, like in beta decay, where a neutron turns into a proton by emitting a low boson.
And its partner?
The Z boson, ZD. Heavier still, about 91.19 GeV. It's electrically neutral. It mediates the neutral current-weak interactions where particles interact via the weak force but don't change charge or flavor, just exchange momentum and energy.
And finding both of these was a huge confirmation.
Monumental. They were discovered at CERN in 1983 with masses exactly where the theory predicted. It was the definitive proof that the electromagnetic and weak forces are unified into a single electroweak force at high energies, a Nobel Prize-winning discovery.
Okay, almost at the top of the elementary ladder. Who's next? The mass giver.
Indeed. The Higgs boson, mass around 125.1 GeV. It's unique, the only fundamental particle found so far with zero spin, a scalar boson. It's the quantum excitation of that all-pervading Higgs field.
And its discovery in 2012 really completed the set for the Standard Model.
But more than that, it confirmed this completely new kind of field exists, one whose non-zero background value fundamentally changes the vacuum and gives mass to almost everything else. It makes the universe we know possible.
So finding the Higgs wasn't just finding another particle, it was confirming a whole mechanism for mass itself.
Exactly, a very profound discovery.
And now, the very top, the heaviest of them all.
The top quark, the undisputed heavyweight champion of elementary particles. Its mass is enormous, around 172.76 GeV.
Wait, 173 GeV. That's huge. Comparable to what?
Comparable to the mass of an entire atom of gold, just one fundamental particle.
Wow. And because mass comes from the Higgs field.
It means the top quark interacts with the Higgs field more strongly than any other known particle. It is the largest coupling to the Higgs.
And it decays incredibly fast.
Insanely fast. Its lifetime is about 5 by 10 year seconds. That's so short it decays before it even has time to bind with other quarks to form a hadron.
So it doesn't get dressed like other quarks.
Correct. It's the only quark we can study in its bare state, free from the messy complications of the strong force confinement. This makes it a unique laboratory for testing fundamental physics, especially the Higgs interaction. It was discovered in 1995 at Fermilab.
What an incredible journey up the ladder, from massless photons to the top quark behemoth.
It really shows the amazing range nature employs.
So we've covered the elementary particles, but you said most of the mass of everyday stuff comes from composite particles, hadrons.
Yes. The particles we actually interact with are mostly hadrons, which are combinations of quarks held together by gluons via the strong force. The most important ones are the baryons, like protons and neutrons.
Right, the proton P and neutron N. You said they make up over 99.9% of visible matter.
That's right. And just to hammer it home, their mass, around 938 MeV for the proton and 939.5 MeV for the neutron, mostly comes not from the mass of their constituent quarks, U for proton, Ed for neutron,
but from the binding energy, the EMCF effect of the strong force.
Exactly. That 99% figure, it's still kind of mind-blowing when you think about it. The solidity of matter is mostly stored energy.
And you also mentioned the tiny mass difference between them is critical.
Absolutely critical. The neutron is just slightly heavier than the proton by about 0.14%. This allows a free neutron to decay into a proton, electron, and antineutrino. If it were the other way around, if the proton were heavier,
hydrogen wouldn't be stable.
Stable hydrogen atoms couldn't exist. Protons would decay into neutrons. The universe would likely be just neutrons, maybe some helium, but no complex chemistry, no stars as we know them, no life. Our existence hangs on that tiny mass difference.
Wow, that's profound. The universe is balanced on a knife edge. Who discovered the neutron again?
James Chadwick in 1932.
Okay, and before the Quark model made sense of it all, there was this particle zoo.
Oh, yes. In the 50s and 60s, particle accelerators were finding dozens and dozens of new hadrons, different types of baryons and mesons, quark-antiquark pairs. It was confusing. Were all these fundamental?
The Quark model brought order.
Beautifully. Gell-Mann and Zweig's idea in 1964 was that all these zoo particles were just different combinations of a few fundamental quarks, initially just up, down, and strange. The model made predictions, most famously the omega minus baryon, which was found shortly after with exactly the predicted properties. A huge triumph.
So the Standard Model, including quarks and the Higgs, has been incredibly successful. But it's not the final word, right? There are gaps.
Big gaps. Despite its successes, the Standard Model is definitely incomplete. As we mentioned, it doesn't include gravity. It offers no particle candidate for dark matter, which we know makes up about 26% of the universe's mass energy.
And dark energy.
Doesn't explain dark energy either, which is about 69%. It can't explain why there's so much more matter than antimatter. And as we said, it doesn't predict its own fundamental constants like particle masses. Those have to be plugged in from experiments.
So these gaps drive the search for new particles beyond the Standard Model.
Exactly. And unlike the early days of just finding whatever popped out of collisions, today's searches are very targeted. Physicists propose new hypothetical particles specifically designed to solve these problems: dark matter, the hierarchy problem, neutrino masses, etc.
What's the most obvious missing piece related to forces? Gravity.
Gravity, yes. A quantum theory of gravity is expected to have a force carrier, the graviton. It should be massless like the photon, but have spin 2, unlike the spin 1 force carriers we know.
Can we detect it?
Probably not directly. Gravity is incredibly weak at the particle level, so the graviton would interact far too feebly. But observing gravitational waves, like LIGO and Virgo do, is a new way to probe gravity's nature, which might eventually give clues about its quantum aspects.
Okay, what about dark matter candidates? You mentioned WIMPs.
WIMPs, weakly interacting massive particles, are a broad category. The idea is they are heavy particles, maybe in the GeV to TeV mass range, that interact only via the weak force and gravity. The appealing thing is, if such particles exist, calculations show they would have been produced in the Big Bang in roughly the right amount to be the dark matter we observe today.
A nice coincidence.
It's a compelling one, yes. The leading WIMP candidate for a long time has come from theories like supersymmetry, the lightest neutralino.
Are there other ideas besides WIMPs?
Oh, yes. Another popular one is the axion. These are hypothetical particles that are extremely light and interact very weakly. They were originally proposed to solve a different problem within the theory of the strong force, the strong CP problem. But it turns out they could also naturally form the cold dark matter we see in the cosmos.
So different candidates trying to solve the same mystery. And you mentioned supersymmetry. SU as Y.
Supersymmetry is probably the most studied extension of the Standard Model. It proposes a new, fundamental symmetry between the two basic types of particles, fermions and bosons.
How does that work?
It predicts that every known particle has a superpartner or sparticle with a spin differing by half a unit. So every quark has a partner called a squark, which is a boson. Every electron has a selectron, a boson. Every photon has a photino, a fermion, and so on.
Doubles the particle count. Why propose such a thing?
Well, it's mathematically elegant, but more importantly, it solves some deep theoretical problems. One is the hierarchy problem, why the Higgs boson is so much lighter than the energy scale where gravity becomes strong. SUSY Y can naturally stabilize the Higgs mass.
And it helps with dark matter.
Yes, if an additional symmetry called R parity holds, the lightest supersymmetric particle, LSP, would be stable, neutral, and weakly interacting, making it a perfect WIMP candidate, often the neutralino I mentioned.
So experiments like the Large Hadron Collider, LHC, are looking for these squarks, selectrons, neutralinos.
Absolutely. That's one of the main goals of the LHC, to produce these heavy, exotic particles predicted by SUSY Y and other beyond standard model theories.
Yet they haven't found them yet.
Not definitively, no. And that's actually really important information, too. The absence of discovery so far rules out certain mass ranges and versions of these theories.
Yeah.
It tells us that if these particles exist, they might be heavier than we initially thought, or hiding in ways we haven't anticipated. The search gets refined, pushed to higher energies or towards more subtle signals.
So even null results are progress.
Absolutely. It narrows down the possibility.
Okay, let's try to wrap this up. We've taken quite a journey looking at the universe through the lens of mass.
We really have, starting from zero with the massless photon and gluon, essential for forces and structure.
Through the almost massless neutrinos, whose tiny mass cracked open the Standard Model.
To the first generation electron, up, down the building blocks of us, and everything's stable.
Then the heavier, unstable copies in the second and third generations, muon, strange, charm, tau, bottom. Still a deep puzzle why they even exist.
Up to the massive W and Z bosons confirming the electroweak unification.
The Higgs boson, the giver of mass itself, confirming a whole new kind of field.
And finally, the incredibly heavy top quark, a unique window into bare quark physics.
It's an amazing hierarchy spanning, 11 orders of magnitude, and much of it's still unexplained by the Standard Model itself.
That's right. The Standard Model is a triumph, incredibly precise where it applies, but its limits are clear now. Neutrino mass, dark matter, dark energy, the matter-antimatter asymmetry, gravity. It doesn't cover the majority of the universe.
So the final thought for our listeners. Where does this leave us?
It leaves us knowing that the particles we've found, as amazing as they are just one part of a much bigger cosmic story, one that's still largely mysterious. That ancient quest, what is everything made of, is far from over. We know the Standard Model isn't the final answer.
There's more out there.
Definitely. Driven by these unanswered questions, the certainty is that there's more discovery waiting in the unseen universe. Pushing the frontiers of energy and observation, what new fundamental truths are lurking just beyond our current reach. That's the exciting part.